The smallest stars in the universe will still be burning 1 trillion years from now, long after every star like our sun has gone dark and cold. Subscribe, there's a new one every few days. This is white space, settle in. For thousands of years, human beings looked up and called the stars eternal, fixed, unchanging. The ancient Greeks named them the apeiron, the boundless, the infinite, and built their cosmologies around the assumption that whatever burned above the atmosphere existed in a realm beyond change, beyond decay, beyond time. It took centuries of careful observation, and ultimately the tools of spectroscopy and nuclear physics to understand what stars truly are, not eternal lights set in a crystalline sphere. Engines, nuclear furnaces of almost incomprehensible scale running on fuel that will eventually run out. Aging and dying on time scales that make the entire history of human civilization look like the blink of an eye measured against the age of the universe itself. What we know now is that stars come in an extraordinary range of sizes, masses, temperatures, and lifespans. Most are modest by cosmic standards. Red dwarf stars, the most common type in the Milky Way, are smaller than our sun, cooler, and burn with such extraordinary frugality that none of them have yet exhausted their hydrogen fuel since the universe began roughly 13.8 billion years ago. The smallest red dwarfs will continue burning for trillions of years. In a real sense, the universe is too young for us to know what a red dwarf looks like when it dies, because none have yet died. They are the long game of stellar evolution, playing out on a schedule that dwarfs anything else we can observe. But at the far end of the spectrum, there are objects that occupy a different extreme entirely. Stars so large that, placed at the center of our own solar system, their surfaces would reach past the orbits of Jupiter or Saturn. Objects whose physical diameters run into the thousands of solar radii, whose luminosities outshine our sun, not by factors of 10 or 100, but by factors of hundreds of thousands, and in the most extreme cases, by factors approaching 1 million. These are the hypergiants, and they are as close to an upper limit of stellar size as nature appears to permit. Canis Majoris sits in the constellation Canis Major, roughly 3,900 light-years from Earth. For much of the 20th century it ranked among the largest known stellar objects, a red hypergiant swelling to a radius somewhere between 1,400 and 2,000 times that of the Sun. The uncertainty in that figure is itself telling. At such distances, and with stellar surfaces that are not hard boundaries, but gradients of luminous plasma, measuring the precise extent of a star is a significant scientific challenge. What is not in doubt is the scale, where Canis Majoris, placed where the Sun is now, its photosphere would extend well past the orbit of Saturn. The Earth, along with Mercury, Venus, Mars, and the entire asteroid belt, would lie deep inside the star. The point where the star's surface ended would be visible from Earth's current position only as the interior of a glowing plasma cloud reaching outward to where the ringed planet now travels. Canis Majoris is also notable for another reason. It is losing mass at a prodigious rate, shedding material through an asymmetric stellar wind that has created a complex nebula of ejected gas around it. Observations with the Hubble Space Telescope revealed this surrounding nebula to be not a simple spherical shell, but a collection of arcs, knots, and filaments, suggesting that the mass loss occurs in bursts rather than smoothly. The star is, in a literal sense, blowing itself apart. Astronomers estimate it has between 17 and 25 times the mass of the Sun, a figure that seems enormous but is actually modest for a hypergiant. The physics of stellar structure mean that the most massive stars are not necessarily the physically largest. Mass and radius for stars are not simply proportional. Hypergiants represent an extreme category within an already extreme class. Supergiants are themselves rare, massive stars that have evolved off the main sequence after burning through their hydrogen fuel with reckless speed. A star like Rachel, the brightest star in Orion, and one of the most intrinsically luminous stars visible to the naked eye, is a blue-white supergiant roughly 70 times the Sun's diameter and 120,000 times its luminosity. By any ordinary measure, Rachel is an extraordinary object. But it is not a hypergiant. Hypergiants are rarer still, defined not only by their enormous physical size but by their extraordinary mass and their proximity to a theoretical threshold above which a star cannot stably exist. This threshold is known as the Eddington limit. It describes the point at which the outward pressure of radiation, the pressure of the photons themselves pushing against the surrounding material, becomes strong enough to overcome the inward pull of gravity. Near this limit, a star becomes inherently unstable. The outer layers, receiving more radiation pressure than gravity can counteract, begin to be driven outward. The star sheds mass, and because shedding mass reduces the total energy output, which reduces radiation pressure, which allows gravity to pull inward again, the system oscillates. Hypergiants near the Eddington limit can exhibit violent, episodic mass loss events, erupting and contracting over timescales of decades or centuries. The most massive stars known today include R136A1, located within the Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way visible to the naked eye from the southern hemisphere. R136A1 carries a mass estimated at roughly 200 solar masses, possibly more. It is so luminous that it emits more energy in 5 seconds than the Sun emits in an entire year. Its ultraviolet radiation is intense enough to ionize hydrogen gas across vast distances, creating the glowing nebula that surrounds it. Massive stars like R136A1 do not merely exist within their environment, they shape it, drive it, and will eventually destroy portions of it when they die. The death of a hypergiant is correspondingly dramatic. When the nuclear fuel in the star's core is finally exhausted, when there is no more hydrogen to fuse into helium, no more helium to fuse into carbon, and the chain of successive burning stages reaches iron, which cannot release energy through fusion, but only absorbs it, the core collapses, not gradually. In a fraction of a second, a core the size of Earth shrinks to a sphere roughly 20 kilometers across. The gravitational energy released in this collapse is staggering, more than the Sun will emit over its entire 10 billion year lifetime, released in seconds. Most of that energy goes into neutrinos, ghostly particles that pass through ordinary matter almost without interaction. A small fraction of it couples to the outer layers of the star, blowing them outward in a supernova explosion. What remains depends on the initial mass of the star. For stars in a certain mass range, the collapsed core becomes a neutron star, an object containing more mass than the Sun, compressed into a sphere you could drive across in a few minutes. In a neutron star, matter is compressed so densely that electrons and protons are forced together into neutrons, creating a state of matter with no analog in any laboratory on Earth. The density at the center of a neutron star is comparable to packing all of humanity into a space the size of a sugar cube. Neutron stars rotate rapidly, some completing hundreds of rotations per second, and emit beams of radio waves from their magnetic poles. When those beams sweep across the Earth like a lighthouse beam sweeping the sea, we detect them as pulsars, the most precise natural clocks in the universe. For the most massive stars, the collapsed core exceeds a threshold beyond which neutron degeneracy pressure itself cannot resist gravity. The core continues collapsing until it becomes a black hole, a region of space-time from which nothing, not even light, can escape. Black holes formed from stellar collapse typically carry masses between a few and a few dozen times that of the Sun. They are detected not by observing them directly, but by observing their effects on surrounding matter, the motion of companion stars, the X-rays emitted by material falling into them, the gravitational waves generated when two black holes spiral together and merge. Gravitational waves were predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. For a century, they remained a theoretical prediction, their existence strongly implied by observations of binary neutron star systems slowly spiraling inward, losing energy in a way that matched perfectly the predicted rate of gravitational wave emission, but never directly detected. Then, on September 14, 2015, the two detectors of the LIGO Observatory registered a signal lasting a fraction of a second. The gravitational wave signature of two black holes, each roughly 30 solar masses, merging at a distance of roughly 1.3 billion light-years. The space-time distortion that reached Earth was so subtle that the mirrors in the detectors were displaced by a distance smaller than 1,000th the diameter of a proton. That we can measure such things at all is a testament to what decades of sustained scientific effort can achieve. The merger of two neutron stars produces a different kind of event. In 2017, LIGO and its European counterpart Virgo detected the gravitational wave signal of two neutron stars spiraling together. And for the first time, astronomers simultaneously observed the electromagnetic light from the same event, a short gamma-ray burst followed by a slowly fading glow called a kilonova. The kilonova proved something that had long been theorized. Neutron star mergers are cosmic forges, synthesizing heavy elements in quantities that supernovae alone cannot account for. The gold in jewelry, the platinum in catalytic converters, the iodine in the human body. These elements were almost certainly forged in neutron star collisions billions of years before the solar system existed. We are, in a very literal sense, assembled from the wreckage of ancient stellar violence. Stellar collisions of a more direct kind occur most frequently in globular clusters, dense, gravitationally bound collections of hundreds of thousands of stars packed into a region only a few hundred light-years across. The nearest globular cluster to Earth, Omega Centauri, is visible to the naked eye from the southern hemisphere as a faint smudge in the sky. It contains roughly 10 million stars in a volume that would fit comfortably between the Sun and its nearest stellar neighbor. In such environments, stars interact gravitationally on timescales of millions of years, and close approaches and outright collisions are not vanishingly rare. These collisions produce what are called blue straggler stars, objects that appear younger and hotter than the surrounding stellar population, because they have effectively reset their clocks by merging with another star. They are anomalies in the color magnitude diagrams of globular clusters, stars that should not exist given the age of the cluster around them, but do exist because stellar mergers have rejuvenated them. A series of stellar collisions within a dense cluster over a short period of time can produce something more dramatic still. Successive mergers create a runaway object of increasing mass, a star growing faster than it can shed material, potentially accumulating hundreds or thousands of solar masses. The end product of such a runaway may be an intermediate mass black hole, a category of black hole between the stellar mass objects created by individual supernovae and the supermassive black holes found at the centers of galaxies. Intermediate mass black holes have been inferred from indirect evidence in several globular clusters, though their existence remains more difficult to confirm than black holes at either extreme of the mass range. At a very different scale, the universe contains structures that challenge our understanding of how matter can organize itself at the largest scales. The distribution of galaxies in the universe is not uniform. Galaxies cluster into groups, groups cluster into superclusters, and superclusters are arranged along filaments and sheets that form a three-dimensional cosmic web with vast, nearly empty voids between them. The Sloan Great Wall, mapped through the Sloan Digital Skies Survey, stretches roughly 1.4 billion light-years across. The Hercules Corona Borealis Great Wall, identified from the distribution of gamma-ray bursts in the distant universe, may span 10 billion light-years or more. Such structures push against the foundational assumption of modern cosmology, the cosmological principle, which holds that viewed at sufficiently large scales, the universe looks roughly the same in every direction and from every location. The existence of structures at billion light-year scales is not necessarily incompatible with this principle. The question is one of degree, of how prominent the structures are relative to the background. But the largest claimed structures have prompted genuine debate about whether our models of large-scale structure formation are missing something. Cosmology is not a settled field. It is an active one with significant open questions about the nature of dark matter, the behavior of dark energy, and the statistical distribution of matter at the largest scales. Closer to home, exoplanet science has in recent decades transformed from a theoretical enterprise into an observational one with a catalog numbering in the thousands. The Kepler Space Telescope, operating from 2009 to 2018, stared at a patch of sky containing roughly 150,000 stars, monitoring them continuously for the tiny dips in brightness caused when a planet passed in front of its star. The resulting catalogue confirmed the existence of thousands of planets and revealed a universe far stranger, far more varied than most astronomers had anticipated before the first exoplanet detections in the 1990s. Among the surprises were the hot Jupiters, gas giants orbiting their parent stars at distances far smaller than Mercury orbits the Sun, completing their years in days or even hours. WASP-12b, located roughly 1,400 light-years away, orbits its star at a distance of about 3.4 million kilometers, completing one orbit every 26 hours. The star's tidal forces act on the planet's extended gas envelope with enough strength to distort it into an egg shape, and the planet loses material continuously, a stream of gas flowing from its upper atmosphere onto the star itself. WASP-12b will be entirely consumed within a few million years. It is, in a very real sense, a planet in the process of being eaten. From a human timescale, this process is imperceptible, but from the perspective of stellar and planetary evolution, it is happening rapidly. The existence of hot Jupiters surprised theorists because the prevailing models of planet formation suggested that gas giants should form far from their stars, where temperatures are low enough for ices to condense and provide the solid building material needed to assemble a planetary core massive enough to gravitationally capture a gas envelope. Under these models, a Jupiter-like planet should not be found orbiting within a few stellar radii of its Sun. The resolution to this apparent contradiction came from the realization that planets do not necessarily stay where they form. Gravitational interactions with the gas disk in which a planet is forming can cause it to migrate inward, sometimes dramatically over timescales of millions of years. The hot Jupiters we observe are survivors of a process of inward migration that stopped, for reasons that are still being worked out, before the planet fell into its star entirely. Some planetary systems exhibit architectural features that are even more striking. The Kepler 444 system, located roughly 117 light-years away, hosts 5 rocky planets orbiting a star nearly 11 billion years old, more than twice the age of the solar system. These planets completed their formation when the universe was less than 3 billion years old. Whatever geological and atmospheric evolution has occurred on them since has had 11 billion years to unfold. What does an 11 billion-year-old rocky planet look like? Whether the extreme age translates to a barren, geologically dead world, or whether long-lived tectonic activity could have sustained hospitable conditions for vast stretches of time, is a question that current technology cannot yet answer definitively. The TRAPPIST-1 system, located 39 light-years from Earth in the constellation Aquarius, has become one of the most intensively studied collections of worlds beyond the solar system. The star at its center is an ultra-cool red dwarf, far smaller and cooler than the Sun, with a radius roughly 1/10 that of the Sun and a surface temperature of about 2,550 degrees Celsius. Its luminosity is about 0.05% of the Sun's. Around it orbit 7 rocky planets, all of them roughly Earth-sized in both radius and mass, and positioned so close to the star that the entire system would fit within the orbit of Mercury around the Sun. 3 of the 7 planets orbit within the classical habitable zone, where temperatures could in principle permit liquid water on a planetary surface. The James Webb Space Telescope launched in December 2021 and reaching its operational orbit roughly 1 million miles from Earth at the L2 Lagrange point, has begun to characterize these worlds in detail. Its infrared instruments can measure the thermal emission from a planet's dayside during the interval when the planet passes behind its star, an event called a secondary eclipse. By comparing the brightness of the star plus planet system before and during the eclipse, astronomers can infer the temperature of the planet's dayside. For TRAPPIST-1b, the innermost planet, initial measurements suggested a dayside temperature consistent with a bare rock receiving intense irradiation with no atmosphere to redistribute heat. For TRAPPIST-1c, the second planet, results similarly point toward the world with at most a thin atmosphere, if it has one at all. These initial results might seem discouraging. But TRAPPIST-1b and 1c are not the planets most likely to be habitable. They are the closest to the star, receiving the most radiation, and were expected to be among the most hostile environments in the system. The 3 planets in the habitable zone designated E, F, and G have not yet been as thoroughly characterized. Their characterization requires more observing time, more telescope cycles, more careful analysis of data accumulated over multiple transits and secondary eclipses. That work is ongoing. What makes the TRAPPIST-1 system uniquely valuable is precisely what makes it challenging. The star is small and cool, which means its planets orbit close to it, which means transits are frequent, which means the system can be studied more efficiently than a comparable system around a Sun-like star. The same factors, the small stellar size, the intense magnetic activity common to red dwarfs, the possibility that the planets are tidally locked with one hemisphere permanently facing the star, also pose obstacles. A tidally locked planet presents its day side to eternal heat and its night side to eternal cold. Whether an atmosphere, if present, could survive and circulate effectively enough to moderate temperatures across both hemispheres is one of the central open questions driving TRAPPIST-1 research. Our own solar system formed from a collapsing molecular cloud roughly 4.6 billion years ago. The process that created it appears to be broadly common across the galaxy, detectable in the structures of protoplanetary disks imaged by the ALMA Observatory in Chile. ALMA's angular resolution is sufficient to reveal rings and gaps in disks around young stars, hundreds of light years away, structures carved by planets in the process of formation, sweeping their orbital lanes clear of debris as they grow. The images are striking in their regularity. Concentric rings, precise gaps, structures that echo, in embryonic form, the architecture of our own solar system. What varies is the mass, composition, and orbital distribution of the planets that emerge, shaped by the initial conditions of the cloud and the stochastic processes of accretion and gravitational scattering. One of the fundamental organizing principles of planetary systems is angular momentum. When a cloud of gas collapses under its own gravity, whatever small net rotation it carries, imparted by the asymmetric gravitational pulls of neighboring clouds, by density fluctuations, by turbulence, is amplified as the cloud contracts. A slowly rotating large cloud becomes a rapidly rotating smaller cloud, just as a spinning skater pulling in their arms rotates faster. The result is that the cloud does not collapse into a point, but into a rotating disk, with material concentrating at the center to form the star, while gas and dust in the surrounding disk gradually coagulate into planets. Because this material all shares the same original sense of rotation, the resulting planets tend to orbit in the same direction and close to the same plane, the flat, orderly geometry that characterizes our solar system, and, to varying degrees, the planetary systems observed around other stars. There are exceptions. WASP 17b is a hot Jupiter whose orbit is retrograde. It circles its star in the opposite direction from the star's rotation, on a highly tilted orbit. The most likely explanation is gravitational scattering, an encounter with another massive planet, or with the stellar companion in the binary system that flung WASP 17b onto its current improbable trajectory. Such scattering events must have been common in the early solar system as well. The outer solar system still shows signs of having been reshuffled. The orbital architecture of the giant planets, the structure of the Kuiper belt, and the existence of a distant reservoir of comets, called the Oort cloud, all point toward a period of gravitational instability early in solar system history, when the giant planets migrated, scattered smaller bodies, and eventually settled into their current orbits. The sun's own behavior has profound consequences for every planet it illuminates. Solar flares, eruptions of energy from regions of intense magnetic activity on the solar surface, release radiation across the electromagnetic spectrum, from radio waves to X-rays. Coronal mass ejections, the largest explosive events in the solar system, hurl billions of tons of magnetized plasma into space at speeds of millions of kilometers per hour. When these ejections are directed toward Earth and interact with the planet's magnetic field, they can drive geomagnetic storms of varying intensity, compressing the magnetosphere on the sunlit side, extending it on the night side, and inducing powerful electrical currents in conductive structures on the ground. The most severe geomagnetic event in the historical record struck in September 1859. Telegraph systems across North America and Europe failed catastrophically. Operators received electrical shocks. Telegraph paper caught fire at stations that had not experienced any equipment malfunction. Some systems transmitted messages with their batteries disconnected, driven entirely by the induced currents from the geomagnetic storm. The aurora borealis was visible across the continental United States, the Caribbean, and as far south as Colombia. Ships at sea reported that their compasses spun erratically. This event, named after the British astronomer Richard Carrington, who observed and documented the associated solar flare, remains the benchmark against which subsequent geomagnetic storms are measured. Evidence preserved in ice cores and tree rings indicates that even the Carrington event was not unprecedented. A solar event in 774 CE, now called the Miyake event, after the Japanese researcher who identified its signature in radiocarbon measurements from tree rings worldwide, produced a spike in atmospheric carbon-14 roughly 12 times larger than the Carrington event. The mechanism that generates such extreme spikes is still debated. Some researchers argue for an exceptionally intense solar flare. Others have proposed, somewhat more controversially, that a gamma-ray burst or some other extrasolar event might have contributed. Whatever the cause, the Miyake event represents a reminder that the space environment around Earth has in the past been far more disturbed than anything recorded in the modern era of electrical infrastructure. The consequences of a Carrington-scale event today would be qualitatively different from those of 1859 because the infrastructure at risk is qualitatively different. Power grids, satellite networks, GPS systems, data centers, submarine communications cables, all are potentially vulnerable to the kind of geomagnetically induced currents that a major storm produces. Transformers in power grids are particularly concerning because they are large, expensive, not interchangeable, and manufactured with lead times of months or years. A storm that destroyed a significant fraction of high-voltage transformers across a continental grid could result in power outages lasting not hours but months. The economic cost and the humanitarian consequences of such an extended outage in a civilization as thoroughly dependent on continuous electrical infrastructure as ours would be difficult to overstate. Scientists who study space weather have called for improved monitoring and early warning systems. The window between a coronal mass ejection leaving the Sun and its impact on Earth's magnetosphere is typically 1 to 3 days, enough time, in principle, to take protective measures, if the threat is taken seriously. The Sun is currently in an elevated phase of its roughly 11-year activity cycle. Sunspot numbers, a proxy for the overall level of magnetic activity, have been rising since the most recent solar minimum in 2019, and the current solar maximum is expected to peak in the mid-2020s before declining again. This means the coming years will be characterized by more frequent solar flares, more coronal mass ejections, and a higher probability of significant geomagnetic disturbances. Satellites in low Earth orbit will experience increased atmospheric drag as the upper atmosphere expands in response to enhanced solar ultraviolet radiation, shortening orbital lifetimes and requiring more frequent altitude corrections. The hundreds of Starlink satellites at low altitudes are among the assets most exposed to these effects. Looking further into the future, much further, the question of whether humanity will ever travel to another star remains open in a way that few large scientific questions do. The nearest stellar system, Alpha Centauri, is 4.24 light-years from Earth. In the units of everyday travel, that is roughly 40 trillion kilometers, the fastest spacecraft ever launched. The Parker Solar Probe, at its closest approach to the Sun, travels at about 690,000 kilometers per hour. At that speed, the journey to Alpha Centauri would take roughly 6,500 years. No mission currently planned and no technology currently under serious development would reduce that to a human lifetime. Proposed concepts for interstellar travel span a wide range of scales and plausibilities. At the most near-term end, the Breakthrough Starshot initiative proposed using a ground-based laser array to accelerate gram-scale light sails to roughly 20% of the speed of light, reaching Alpha Centauri in about 20 years. The physics is valid. The engineering challenges are formidable in ways that are not merely matters of scale, but of fundamental difficulty. The laser array would need to deliver gigawatts of power to a target the size of a postage stamp with extraordinary precision, and the sail would need to survive the thermal and mechanical stresses of that acceleration without being destroyed. The probe would have roughly 20 minutes in the Alpha Centauri system before traveling on, and would need to transmit data back across 4.24 light-years on a power budget measured in milliwatts. Nuclear propulsion represents a different approach. Nuclear pulse propulsion, studied under Project Orion in the 1950s and 1960s, proposed propelling a spacecraft by detonating a series of small nuclear bombs behind a large pusher plate. The concept was physically sound simulations and small-scale tests with conventional explosives confirmed the basic mechanics. But it was killed by the Limited Test Ban Treaty of 1963, which prohibited nuclear explosions in space. More recent concepts involve nuclear fusion, using the energy of fusion reactions to heat and accelerate the propellant to exhaust velocities far beyond what chemical rockets can achieve. The specific impulse, a measure of propellant efficiency of a fusion drive, would far exceed anything currently operational. The obstacle is that sustained, controlled nuclear fusion has been pursued in laboratories on Earth for 70 years without yet producing a commercially viable energy source. Though recent progress at the National Ignition Facility and various private ventures suggests that the gap is narrowing. Between the optimistic proposals and the sobering engineering realities lies a third consideration, which is biological and sociological rather than technical. Even if a spacecraft could be built capable of reaching a nearby star within a human lifetime, traveling at a significant fraction of the speed of light, the question of what its occupants would find and what they could usefully do there remains largely unanswered. We do not yet know whether any of the planets in the Alpha Centauri system are habitable or inhabited, or whether the Proxima Centauri planet in the habitable zone has an atmosphere or liquid water, or anything that would justify the journey. The James Webb Space Telescope and its successors may begin to answer those questions from Earth before any physical spacecraft could arrive, and yet the impulse behind the question is real and will not diminish. The stars that burn in the night sky are not distant lanterns. They are suns, many of them surrounded by worlds, some of those worlds potentially harboring conditions that could support something like what we would recognize as life. The distance between here and there is real, and it is vast, and nothing in physics offers us a shortcut through it. But the history of science is, among other things, a history of making accessible what once seemed permanently out of reach. People who sailed by that reckoning across open ocean could not have imagined the communications satellite that makes their descendants' navigation trivially easy. The gap between what exists now and what will be needed for interstellar travel is real. So was every other gap that has since been closed. The stars have been burning for billions of years. They will continue burning for billions more. The largest of them, the hypergiants, will live for a few million years and die in fires that seed the galaxy with the atoms of which everything else, planets, oceans, living organisms, will eventually be made. The smallest will outlast the current age of the universe by a factor of 1,000. In the vast middle of that range, our own sun will burn quietly for another 5 billion years, warming a small planet on one of the Milky Way spiral arms, while the beings on that planet continue the project of understanding where they are, what surrounds them, and how eventually they might reach it. To understand why the scale of these objects matters, why it is worth dwelling on the numbers rather than simply accepting them as large, it helps to try, briefly, to make them concrete. The Sun contains 99.8% of all the mass in the solar system. Everything else, all 8 planets, their moons, the asteroid belt, the Kuiper belt, the Oort cloud, amounts to the remaining 0.2%. The Sun is so massive that its gravity controls the orbits of objects tens of thousands of times farther from it than the Earth. Its light takes 8 minutes to reach us and over an hour to reach Neptune. The Sun is not a small object, and yet a hypergiant like Vi Canis Majoris contains roughly 17 to 25 times as much mass, spread across a volume so large that if you could somehow travel at the speed of light through the star's interior, the journey from one side to the other would take several hours. Hours at the speed of light through a single star. The light travel time is a useful measure, because it is intuitive in a way that raw numbers often are not. Light travels 300,000 kilometers every second. It crosses the diameter of the Earth in roughly 42 milliseconds. It crosses the distance from Earth to Moon in about 1.3 seconds. And it would take several hours to traverse the interior of the largest known stellar objects. These are not just large. They are large in a way that puts the most extreme human engineering, mountains, cities, continents, into a category so small it barely registers. The physics that allows such objects to exist is also the physics that limits how large they can get. Above a certain mass, the radiation pressure from a star's core becomes strong enough to overcome the inward pull of gravity and disperse the outer layers. This is not a hard line, but a regime. Stars approaching and exceeding the Eddington limit exist, but they are violently unstable, shedding mass rapidly and episodically rather than existing in any steady state. Eta Carinae, roughly 7,500 light-years from Earth, is perhaps the most famous current example. In the 1840s, it underwent a massive eruption, briefly becoming the second brightest star in the night sky, while expelling several solar masses of material into the surrounding nebula. It did not explode as a supernova. It survived, but in a diminished state. Its current luminosity is thought to be several million times that of the Sun, making it one of the most intrinsically luminous objects in the Milky Way. It is expected to produce one of the most spectacular supernovae in recent galactic history at some point in the geologically near future, an event that from Earth's distance may be visible in daylight for weeks. The study of stellar populations in different types of galaxies reveals how environment shapes the stars that form within it. Elliptical galaxies, the large, smooth, reddish island universes that populate the centers of galaxy clusters, are dominated by old, low-mass stars. They contain little cold gas and dust from which new stars could form. The massive, luminous blue stars that characterize active star-forming regions are absent. The color of an elliptical galaxy encodes its history. It is red because the blue and ultraviolet light of hot massive stars has long since been extinguished. Those stars lived their brief, brilliant lives and died when the galaxy was young, and nothing has replaced them. Elliptical galaxies are graveyards for the stellar populations of their youth. Spiral galaxies like the Milky Way are different. Their disk contains cold molecular gas and dust concentrated along the spiral arms, which serve as the sites of ongoing star formation. The blue tint of spiral arms is the light of hot young stars, O and B-type giants that will live for only a few million years before exploding. In the interarm regions and in the central bulge, the stellar population is older, redder, less massive on average. A spiral galaxy is a system in which new generations of stars are continuously born from material enriched by the deaths of earlier ones. Each supernova seeds the surrounding interstellar medium with the heavy elements synthesized in the star's interior: carbon, nitrogen, oxygen, silicon, iron, raising the metallicity of the gas from which subsequent generations of stars and planets will form. The Sun and its planets formed from gas that had already been processed through multiple stellar generations. We are, in the standard phrase, made of recycled stardust. Galaxy classification itself has a history worth briefly tracing. Edwin Hubble's 1926 scheme, dividing galaxies into ellipticals, spirals, barred spirals, and irregulars, was based purely on morphology, what galaxies look like through a telescope. It has survived for nearly a century because it continues to capture something real about the underlying physics. The division between elliptical and spiral galaxies corresponds roughly to a division between quiescent and actively star-forming systems, which in turn corresponds to a division in the history of gas content, merger history, and the environments these systems inhabit. Galaxies in the dense cores of clusters tend to be elliptical. Galaxies in lower density field environments tend to be spiral. The process by which a spiral galaxy star formation is shut off, quenched in the terminology, and it transforms into a red gas-poor elliptical is called galaxy evolution, and it is one of the central research programs of modern observational astronomy. Active galactic nuclei, the luminous centers of galaxies powered by accretion onto supermassive black holes, represent another dimension of galactic life. In the most extreme cases, the light from the accretion disk outshines the entire rest of the galaxy by factors of hundreds. These are the quasars, seen predominantly at high redshifts and therefore great distances, meaning they were most common when the universe was young. The most distant quasars known have been observed at redshifts, placing them within the first billion years after the Big Bang. The black holes powering them, some carrying billions of solar masses, somehow assembled themselves in a period that seems uncomfortably short, given what we understand about how black holes grow. The formation of supermassive black holes in the early universe remains one of the genuinely open problems in astrophysics. Closer and more accessible are the active galactic nuclei in nearby galaxies. Centaurus A, one of the nearest radio galaxies to the Milky Way, harbors a supermassive black hole of roughly 55 million solar masses. Jets of material accelerated to near the speed of light emerge from the central region and extend for hundreds of thousands of light years, terminating in enormous radio lobes that dwarf the visible galaxy itself. The mechanisms by which these jets form, collimate, and propagate across such extraordinary distances are still incompletely understood. They represent some of the most energetic sustained outflows in the known universe, and they interact with the surrounding intergalactic medium in ways that affect the subsequent evolution of the entire galaxy cluster. The relationship between supermassive black holes and their host galaxies is one of the more surprising discoveries of the past 3 decades. The mass of the central black hole in a galaxy correlates tightly with properties of the galaxy's bulge, its total stellar mass, the velocity dispersion of its stars, despite the fact that the black hole's gravitational influence extends only a tiny fraction of the galaxy's total size. The black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses, and its gravitational sphere of influence covers only a few light years. The Milky Way itself is roughly 100,000 light years across. And yet the mass of the black hole and the properties of the stellar bulge are correlated. This correlation implies that supermassive black holes and their host galaxies co-evolve, that they grow together, influence each other, regulate each other through feedback mechanisms that are still being mapped in detail. The Event Horizon Telescope, a planet-scale interferometric array that combines radio observatories from across Earth into a single instrument with angular resolution approaching that of a space-based telescope, produced the first images of the shadows of supermassive black holes, first M87R in 2019, then Sagittarius AR in 2022. These images show a bright ring of emission surrounding a dark central region. The photon ring, formed by light orbiting just outside the event horizon, and the shadow, the region where the black hole's gravity captures all photons that approach too closely. The size of the shadow, roughly 50 microarc seconds for M87, smaller than the apparent size of a golf ball on the Moon, required baselines stretching from Chile to Greenland, from Hawaii to the South Pole, and coordinated observations across multiple observatories operating at millimeter wavelengths simultaneously. The images confirmed predictions of general relativity in an extreme gravitational regime that no other test could access. The next generation of large telescopes, both on the ground and in space, will extend these capabilities substantially. The extremely large telescope currently under construction on Cerro Amazonas in Chile will have a primary mirror 39 meters across, roughly the diameter of a 10-story building. Its angular resolution will be sufficient to image the surfaces of nearby stars, resolve protoplanetary disks in star-forming regions at distances where current instruments see only point sources, and characterize the atmospheres of nearby exoplanets through spectroscopic observations during transits. The 30-meter telescope, if completed at its proposed site on Mauna Kea in Hawaii, will have comparable capability The Roman Space Telescope, a wide-field infrared observatory scheduled for launch in the late 2020s, will conduct surveys of the sky orders of magnitude faster than Hubble, cataloging millions of galaxies, identifying thousands of new exoplanets through microlensing, and enabling statistical studies of dark energy through the geometry of the large-scale structure. The universe that these instruments will reveal will not overturn what we already know. The fundamental picture, a universe 13.8 billion years old, expanded from an initially hot, dense state filled with galaxies, stars, and the planets and molecules that form around them, is robust. What will change is the resolution of the picture, the ability to see smaller structures, trace fainter signals, characterize the compositions and temperatures of distant worlds. The question of whether any of those worlds harbor life, whether the conditions that gave rise to biology on Earth are common or rare across the billion-year history of the observable universe, will be addressed empirically rather than just philosophically for the first time. That question is, in a sense, the one that subsumes all the others. The sizes of stars, the architectures of planetary systems, the physics of stellar death and galaxy evolution, the behavior of the sun, the possibility of interstellar travel, all of these converge on a single question that human beings have asked in various forms as long as we have been capable of abstract thought. Are we alone? Not in the sense of any particular theology or mythology, but in the empirical, testable sense. Is the chemistry that produced DNA, cells, and eventually nervous systems capable of modeling the universe around them? Is that chemistry a fluke that occurred once, here on this particular planet, orbiting this particular star in one of a few 100 billion galaxies? Or is it a generic outcome that follows, given sufficient time and the right conditions, from the laws of physics as we understand them? The honest answer is that we do not know. We have a sample size of one confirmed biosphere. We have strong theoretical reasons to think that the basic chemistry of life, carbon-based molecules in liquid water, driven by energy gradients, should occur wherever the conditions are met. We have no confirmed detection of life anywhere beyond Earth, and no confirmed detection of a biosphere resembling Earth. The absence of evidence is not evidence of absence, particularly when our ability to detect atmospheric biosignatures on exoplanets is in its earliest infancy. What the next generation of telescopes will provide for the first time is a genuine search, one with the sensitivity and specificity to detect certain kinds of atmospheric signatures on nearby Earth-sized planets, if they are present. If the answer turns out to be positive, if we find in the spectrum of some distant atmosphere a chemical imbalance that can only be maintained by ongoing biological activity, it will be among the most significant discoveries in the history of science. And if the answer after exhaustive search is negative, if we find world after world that is barren, however habitable it might appear, that too will be a result of profound importance, forcing a reconsideration of assumptions so basic they are rarely even articulated. Either way, the universe being probed is the same one that was visible to the first humans who looked up. It has not changed. What has changed is our ability to look carefully, to interpret what we see, and to understand the scale of what surrounds us. The stars are not eternal, they are not fixed. They are born from the collapse of gas clouds, burn through their fuel on schedules determined by their mass, and die in ways that leave behind the material from which subsequent stars and planets and apparently living things are assembled. We are part of that process. The iron in hemoglobin, the calcium in bone, the oxygen in every breath, all of it was forged in stars that lived and died before the sun existed. We are not observers of the cosmos looking in from outside. We are what the cosmos does in certain places, under certain conditions, given enough time. There is a version of the story of stellar astronomy that begins with the naked eye and ends with the Event Horizon Telescope. And in that telling, it is a story of instruments getting bigger and better, while the objects they study stayed where they were. But that is not quite right. The objects have changed too, at least in our understanding of them, and the changes have not been uniform improvements on earlier knowledge. They have sometimes been corrections, reversals, moments when a concept that seemed secure turned out to be inadequate to the phenomena it was meant to describe. The classification of stars by spectral type, the OBF-GKM sequence, extended in recent decades to include the even cooler L, T, and Y dwarfs, is one of the great achievements of late 19th and early 20th century astrophysics. It was developed largely through the work of women astronomers at the Harvard Observatory, most prominently Annie Jump Cannon, who classified hundreds of thousands of stellar spectra by hand. The classification scheme organizes stars by surface temperature, which in turn correlates with color. O-type stars are blue-white and extremely hot, with surface temperatures above 30,000 degrees Celsius. M-type stars are red and cool, with surface temperatures around 3,000 degrees or below. Our Sun, a G-type star, sits comfortably in the middle, with a surface temperature of roughly 5,500 degrees. The original motivation for the classification was empirical. Here are the spectra. Here are the patterns. Here is a scheme that organizes the patterns. The physical explanation came later, primarily through the work of Cecilia Payne-Gaposchkin, whose 1925 doctoral dissertation showed that the differences in stellar spectra arise not from differences in the chemical composition of stars, but from differences in temperature. Stars, Payne-Gaposchkin demonstrated, are overwhelmingly composed of hydrogen and helium. The spectral differences, the presence or absence of particular absorption lines, reflect how energetically the atoms in the stellar atmosphere are being excited, which depends on temperature, not primarily on composition. This was not the accepted view at the time. Her supervisor, Henry Norris Russell, initially persuaded her to soften her conclusions because they contradicted prevailing opinion. He later confirmed her result independently and published it himself, a piece of scientific history that has been much revisited since. Her work stands as one of the most important results in the history of astrophysics. The Hertzsprung-Russell diagram, developed independently by the Danish astronomer Ejnar Hertzsprung and the American Henry Norris Russell in the early 20th century, plots stars by luminosity against surface temperature and reveals that most stars fall along a diagonal band called the main sequence. Stars on the main sequence are fusing hydrogen to helium in their course. The position of a star on the main sequence depends on its mass. Massive stars sit at the top left, luminous and hot. Low-mass stars sit at the bottom right, dim and cool. The Sun sits roughly in the middle. Stars leave the main sequence when they exhaust the hydrogen in their cores. What happens next depends again on mass. Low-mass stars, like the Sun, expand into red giants, fusing helium in a shell around an inert carbon-oxygen core, eventually shedding their outer layers to form a planetary nebula around a cooling white dwarf. Higher mass stars expand more dramatically, reaching the supergiant and ultimately hypergiant regime before dying in core collapse supernovae. The Hertzsprung-Russell diagram is not just a classification scheme. It is a map of stellar evolution, a way of reading the past, present, and future of any star from its current observable properties. White dwarfs, the endpoints of stellar evolution for the majority of stars in the galaxy, are objects of remarkable physics. Compressed to roughly Earth's size, but containing the mass of the Sun, they are supported against further gravitational collapse, not by thermal pressure. They are no longer generating energy through nuclear fusion, but by electron degeneracy pressure. a quantum mechanical phenomenon arising from the Pauli exclusion principle. Electrons, being fermions, cannot occupy the same quantum state. When matter is compressed sufficiently, all available low-energy states become filled, and further compression requires pushing electrons into higher energy states, generating a pressure that resists it. This pressure is independent of temperature. A white dwarf cools slowly over billions of years while its internal structure remains unchanged. The limiting mass above which electron degeneracy pressure cannot support a white dwarf was calculated by the Indian physicist Subrahmanyan Chandrasekhar in 1930 at roughly 1.4 solar masses. Above this limit, called the Chandrasekhar limit, the white dwarf will collapse. This limit has profound consequences for type Ia supernovae. When a white dwarf in a binary system accretes mass from a companion and approaches the Chandrasekhar limit, runaway carbon fusion ignites throughout its interior and the star is destroyed entirely in a thermonuclear explosion. Because the mass at the time of explosion is always close to the same value. The peak luminosity of these explosions is also always similar, making them useful as standard candles for measuring distances across the universe. It was through observations of type AA supernovae at large distances that two teams of astronomers in 1998 discovered that the expansion of the universe is accelerating. Objects at high redshift appeared fainter than they should have been if the universe's expansion were slowing down under gravity. The implication was that something now called dark energy is driving the expansion to speed up. The nature of dark energy remains unknown. It may be a property of space-time itself, a cosmological constant of the kind Einstein introduced and then famously withdrew. It may be something more exotic, a scalar field that evolves over time. Distinguishing between these possibilities is one of the primary scientific goals of several current and planned observatories, including the Euclid satellite launched in 2023 and the Vera Rubin Observatory being completed in Chile. Dark matter presents a parallel puzzle at a different scale. The rotation curves of spiral galaxies, measurements of how fast stars at different distances from the galactic center are orbiting, do not follow the pattern that would be expected if the only mass present were the visible stars and gas. Stars in the outer reaches of galaxies orbit just as fast, in many cases faster, than simple Newtonian gravity from the visible mass would predict. The inference is that there is additional invisible mass distributed throughout the galaxy in an extended halo dark matter. Its presence is also inferred from the bending of light by galaxy clusters, which exceeds what the visible mass could account for, and from the pattern of temperature fluctuations in the cosmic microwave background, which encodes information about how matter was distributed in the universe when it was only 380,000 years old. Dark matter does not emit or absorb light, does not interact through the electromagnetic force, and cannot be detected by any conventional astronomical instrument. It interacts only through gravity or possibly through some additional force much weaker than electromagnetism. Numerous particle physics candidates have been proposed over the decades, including weakly interacting massive particles, actions, sterile neutrinos, and more exotic possibilities. Several major experimental programs, including underground detectors designed to register the occasional nuclear recoil from a dark matter particle passing through a crystal, have produced null results. The dark matter, if it is a particle or collection of particles as most physicists assume, has proven extremely difficult to catch. Its distribution throughout the universe is mapped precisely enough through its gravitational effects. Its identity remains unknown. The cosmic microwave background is perhaps the most important single dataset in cosmology. It is the thermal radiation left over from the epoch of recombination, when the universe had cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, photons scattered continuously off free electrons and could not travel freely. After recombination, roughly 380,000 years after the Big Bang, the universe became transparent, and the photons that had been trapped in the plasma were free to travel. They have been traveling ever since. They arrive at our detectors today from every direction. Their original temperature of about 3,000 degrees redshifted by the expansion of the universe to just 2.7 degrees above absolute zero, the microwave band. The cosmic microwave background is not perfectly uniform. It contains temperature fluctuations at the level of about 1 part in 100,000 tiny variations that reflect the density fluctuations present in the early universe. These fluctuations are the seeds of large-scale structure. Over billions of years, gravity amplified the slightly denser regions into galaxies, galaxy clusters, and the filamentary cosmic web. The detailed pattern of the fluctuations encodes information about the geometry, composition, and expansion history of the universe. The analysis of that pattern, carried out most precisely by the Planck satellite, which operated from 2009 to 2013, has given us the values of the cosmological parameters that define our standard model. The universe is 13.8 billion years old, it is spatially flat, it is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The precision of these measurements is remarkable. The age of the universe is known to better than 1%. The Hubble constant, the rate at which the universe is expanding, is known from the cosmic microwave background to high precision. And yet there is a problem. The value of the Hubble constant inferred from the cosmic microwave background does not agree with the value measured directly, using type Ia supernovae and other distance indicators in the local universe. The discrepancy is small in absolute terms, but large in statistical significance. The two measurements, each done carefully and checked repeatedly, simply disagree. This is called the Hubble tension, and it has been growing more significant as the measurements have become more precise. It may reflect a systematic error in one or both measurements. It may reflect new physics beyond the standard cosmological model, a modification of dark energy, a previously unknown particle species, something else entirely. As of the mid-2020s, it remains unresolved. The Big Bang itself, the hot, dense initial state of the universe from which the current structure emerged, is sometimes described as if it were an explosion, a point in space where something went off and stuff flew outward. This is misleading in an important way. The Big Bang was not an explosion in space, it was an expansion of space. There was no center, no edge, no surrounding void into which the universe expanded. Every point in the universe was, at the moment of the Big Bang, in the same place as every other point, and the expansion carried every point away from every other point simultaneously. The universe was not smaller at the Big Bang in the sense of being more confined in a pre-existing space. It was smaller in the sense that distances between all points were smaller by a large factor, currently estimated at roughly 1,000 for the cosmic microwave background epoch, and arbitrarily large for earlier times. What, if anything, preceded the Big Bang is not something current physics can address. The equations of general relativity predict a singularity, a point of infinite density at the beginning of the universe. But singularities in physical theories are generally understood as signs that the theory is being pushed beyond its range of validity rather than as descriptions of physical reality. A complete theory of quantum gravity, one that reconciles general relativity with quantum mechanics, would presumably be able to say something about what, if anything, happened before or at the Planck time. Roughly 10 to the minus 43 seconds after the mathematical beginning of the Big Bang. No such theory currently exists in complete form, though significant progress has been made along several lines, including string theory and loop quantum gravity. The inflationary hypothesis, developed in the 1980s, primarily by Alan Guth, proposes that the very early universe underwent a period of exponential expansion, inflation, during which a small, causally connected region of space expanded by a factor of at least 10 to the 26 or more in a tiny fraction of a second. Inflation explains several features of the universe that would otherwise appear as remarkable coincidences. The near-perfect spatial flatness, the uniformity of the cosmic microwave background across regions of the sky that should not have been in causal contact, and the absence of magnetic monopoles predicted by grand unified theories. Inflation also generates quantum fluctuations that are stretched to macroscopic scales and become the seeds of large-scale structure. The pattern of fluctuations predicted by simple inflationary models matches the observed cosmic microwave background with impressive accuracy. But inflation, while predictively successful, is not a unique theory. There are hundreds of inflationary models, differing in the details of the scalar field, the inflaton that drives the expansion. Most of them make predictions that are observationally nearly indistinguishable from one another. The clearest discriminant would be the detection of primordial gravitational waves, waves generated by inflation itself, imprinted in the polarization of the cosmic microwave background. Several experiments are currently searching for this signal. It has not yet been detected. Its detection, if it occurs, would provide a direct observational window into the physics of the earliest moments of the universe. The formation of the first stars in the universe is a subject of active research that sits at the intersection of cosmology and stellar astrophysics. After recombination, the universe was filled with neutral hydrogen and helium. There were no stars, there were no galaxies, there was structure, the slightly denser regions that would eventually collapse into galaxies, but nothing was yet luminous. This period is called the Cosmic Dark Ages, and it lasted for somewhere between 100 million and 400 million years after the Big Bang. The first stars to form designated population 3 stars by convention. Though they were the first generation rather than the third, were qualitatively different from any stars that exist today. They formed from gas that had not yet been enriched with heavy elements. The only elements available in significant quantities were hydrogen and helium, with trace amounts of lithium produced during Big Bang nucleosynthesis. Without the metals that serve as coolants in contemporary star-forming regions, allowing gas clouds to cool efficiently and fragment into small clumps. The first star-forming clouds cooled more slowly. They tended to collapse into more massive objects. The best current simulations suggest that population 3 stars were typically very massive, possibly hundreds of solar masses, potentially approaching or exceeding 1,000 solar masses in some cases, far above the mass range of any stars we observe in the modern universe. These stars would have been extraordinarily luminous. A star of several hundred solar masses produces ultraviolet radiation, intense enough to ionize the hydrogen gas for thousands of light years in every direction, creating a growing sphere of ionized plasma, an HII region around it. When many such stars formed across the universe, their collective ultraviolet radiation began to re-ionize the neutral hydrogen that had recombined 380,000 years after the Big Bang. This process, called cosmic re-ionization, occurred primarily between about 400 million and 1 billion years after the Big Bang, and it fundamentally changed the large-scale character of the intergalactic medium. The universe transitioned from one in which most hydrogen was neutral and opaque to ultraviolet light, to one in which most hydrogen was ionized and transparent. We live in the re-ionized universe. The intergalactic medium today is almost completely ionized by the ultraviolet background generated by stars and quasars. No population 3A star has ever been directly observed. They are expected to have been extremely short-lived, a star of several hundred solar masses burns through its fuel in perhaps 1 million years or less, and the earliest epochs of the universe at redshifts above about 10 are only now becoming accessible to observation with the James Webb Space Telescope. Webb has detected galaxies at redshifts above 14, corresponding to a time when the universe was less than 300 million years old, and has found evidence for stars with unusual chemical compositions that may reflect formation from relatively metal-poor gas. The hunt for genuinely population 3 stellar spectra stars composed only of hydrogen and helium continues. Their detection would be a direct observational window into the conditions of the earliest stellar generation. The death of population 3 stars was itself consequential. The most massive of them, dying as core collapse supernovae or pair instability supernovae, a category of explosion possible only at very high stellar masses, in which the core becomes hot enough for electron-positron pair production to drain energy and trigger collapse before the usual nuclear burning sequence completes, distributed the heavy elements they had synthesized into the surrounding gas. Carbon, oxygen, silicon, iron, and the full suite of elements up to the iron peak were dispersed into the intergalactic and circumgalactic medium. The second generation of stars, population 2, formed from this gas and was already metal-enriched compared to the pristine population 3 material, though still metal-poor compared to the Sun. The oldest stars in the Milky Way's halo are population 2 stars. Some of them formed over 13 billion years ago, their chemical compositions preserving a record of the nucleosynthesis that occurred in the first stellar generation. The study of the chemical abundances of the oldest stars in the Milky Way, a field called stellar archaeology or near-field cosmology, provides some of the most direct empirical constraints on the properties of population 3 stars and their supernovae. The abundance patterns of iron, carbon, oxygen and other elements in metal-poor halo stars encode information about the masses and explosion energies of the stars that produce those elements. Certain patterns, high carbon abundance relative to iron, for example, are signatures of specific types of population 3 supernovae. Comparing these patterns to the predictions of nucleosynthesis models allows astronomers to reconstruct statistically the properties of the first stellar generation from the chemical record left in the oldest surviving stars. It is a form of forensic astronomy, reading the past from chemistry rather than from direct observation. Planetary science within our own solar system provides a set of case studies in the variety of outcomes possible from similar initial conditions. The 8 planets formed from the same disk of gas and dust around the same star within roughly the same period of time. Yet they are profoundly different from one another in almost every respect: size, mass, composition, atmosphere, surface conditions, geological activity, and potential for life. Understanding why requires tracing the processes of accretion, differentiation, bombardment, volatile delivery, and atmospheric evolution that operated over the first billion years of solar system history. The terrestrial planets, Mercury, Venus, Earth, and Mars, formed primarily from rocky and metallic material in the inner solar system, where temperatures in the protoplanetary disk were too high for water ice to condense. The giant planets, Jupiter, Saturn, Uranus, and Neptune, formed farther out, where ices could contribute to the solid material available for planetary embryos, allowing cores to grow massive enough to capture large gaseous envelopes from the disk before the disk dissipated. The boundary between these two regimes, called the snow line or ice line, was located at roughly 2.5 to 3 astronomical units from the Sun, in the region of the asteroid belt, which preserves a population of planetesimals that never coalesced into a full planet, partly because of Jupiter's gravitational influence. Jupiter itself is the dominant gravitational presence in the solar system after the Sun. Its mass, about 318 times that of Earth, gives it a gravitational influence that shapes the orbits of everything from the asteroid belt to the Kuiper belt. The early Jupiter likely played a significant role in delivering water to the inner solar system. Current models suggest that the rocky planets of the inner solar system formed relatively dry. The temperatures at their formation distances were too high for water ice to be a significant constituent of the solid material. The water on Earth, crucial for the chemistry of life, was probably delivered later, during a period of intense bombardment, when small bodies from the outer solar system, scattered inward by the migration of the giant planets, brought water and other volatiles to the terrestrial planets. The same bombardment that brought water also brought carbon compounds, organic molecules that may have been precursors to the chemistry of life. Mars occupies a special place in discussions of planetary habitability because it provides our closest example of a world that may once have been more habitable than it is today. Orbital imagery and rover investigations have documented the existence of ancient river valleys, lake beds, and delta deposits, features that can only have formed by the sustained flow of liquid water on the surface. The Perseverance rover, operating in Jezero crater since 2021, is exploring what was once a lake that persisted for millions of years. The chemical and mineralogical signatures in the rocks record the conditions of that ancient environment, the pH of the water, the temperature range, the presence of organic molecules. The rover is collecting samples that a future mission is intended to return to Earth for detailed laboratory analysis. Those samples, when they arrive, will represent the most direct physical evidence yet examined for the conditions that existed in Mars's habitable past. Why Mars is no longer habitable is a question with a largely understood answer. Mars is smaller than Earth. Its mass is only about 10% of Earth's, and it cooled more rapidly. A smaller planet loses its internal heat faster, because the ratio of surface area to volume is larger, and heat escapes through the surface. As Mars cooled, its internal magnetic dynamo shut down. Without a global magnetic field, the upper atmosphere of Mars was no longer shielded from the solar wind, the continuous stream of charged particles flowing outward from the Sun. Over hundreds of millions of years, the solar wind gradually stripped away the Martian atmosphere. The atmospheric pressure at the Martian surface today is less than 1% of Earth's liquid water cannot exist stably at the surface under these conditions. The planet that once had lakes and rivers is now a cold, dry desert with an atmosphere so thin that the sky is nearly always clear. Venus presents a different cautionary tale. It is nearly identical to Earth in size and mass. The two planets are sometimes called twins, and it formed at a similar distance from the Sun. Yet its surface is a hellscape. Surface temperatures around 465 degrees Celsius, an atmospheric pressure 92 times that of Earth's at sea level, clouds of sulfuric acid, and no evidence of liquid water anywhere. Venus almost certainly had water early in its history. The question of where it went is tied to the question of whether Venus ever had a stable temperate climate in the first place. The leading hypothesis is that Venus experienced a runaway greenhouse effect. As the young sun-brightened stars increase in luminosity over their lifetimes, and the Sun was roughly 30% less luminous 4 billion years ago than it is today, the warming of Venus's surface began to drive water vapor into the atmosphere. Water vapor is a greenhouse gas, and its presence caused further warming, driving more evaporation in a feedback loop that eventually boiled away the oceans entirely. Once in the upper atmosphere, water molecules were dissociated by ultraviolet radiation, and the hydrogen was lost to space while the oxygen reacted with surface rocks. The result was a planet with almost no water and an atmosphere dominated by carbon dioxide, which drove temperatures to their current extreme levels through an intense greenhouse effect. Venus is a warning about the stability of planetary climates and the narrow range of conditions under which liquid water can persist on a rocky planet over geological timescales. Understanding habitability in the solar system context sets the stage for evaluating habitability beyond it. When astronomers measure the temperature of an exoplanet, or constrain its atmospheric composition, or estimate its bulk density and infer something about its interior structure, they are doing so within a framework built from the comparative planetology of Mercury, Venus, Earth, Mars, and the giant planets. The solar system is the calibration dataset. The diversity within it, the contrast between Earth and Venus, between Mars and Earth, between the gas giants and the rocky planets, is a reminder that the outcome of planet formation is not deterministic from the initial conditions alone. Small differences in mass, orbital distance, initial water content, and the timing of giant planet migration can produce radically different worlds from similar starting materials. This sensitivity to initial conditions has implications for the frequency of genuinely Earth-like planets. It is not enough for a planet to be in the habitable zone, the range of distances from its star, where liquid water could exist on the surface. The planet also needs to be the right size, with the right interior heat budget to sustain geological activity and the right rate of cooling. It needs to have a magnetic field robust enough to protect the atmosphere from stellar wind erosion. It needs a source of volatile delivery. It needs perhaps a large moon like Earth's to stabilize its axial tilt and prevent the kind of obliquity variations that could produce catastrophic climate swings. It may need the gravitational presence of a Jupiter-like planet at the right distance to deflect potentially sterilizing impactors. Each of these conditions can be individually examined in the exoplanet population as observational capabilities improve. Together they define something much narrower than the simple habitable zone. The chemistry of life as we know it is built on carbon. Carbon forms stable covalent bonds with a wider variety of other elements, and at a greater range of temperatures and pressures than any other element. It can form chains, rings, and branched structures of essentially unlimited complexity. It dissolves readily in water and participates in the reactions that store and release chemical energy. The organic chemistry that underlies biology, amino acids, nucleotides, lipids, sugars, is almost entirely carbon-based. Whether life elsewhere might be built on a different chemical foundation is a genuine scientific question, though silicon is the only element with comparable bonding versatility, and silicon-based complex chemistry is far more limited in scope, under conditions that occur naturally in the universe. The building blocks of life's chemistry are widely distributed in the cosmos. Amino acids have been found in carbonaceous chondrite meteorites, the most chemically primitive class of meteorite, which formed from material in the protoplanetary disk of the early solar system before being disrupted. These meteorites contain hundreds of distinct amino acid species, including the 20 that life on Earth uses for protein construction, and hundreds more that life does not use. Complex organic molecules have been detected in the interstellar medium, formaldehyde, ethanol, glycolaldehyde, metal formate, synthesized on the surfaces of cold dust grains in molecular clouds. Phosphorus compounds, sugars, and other molecules central to biochemistry have been identified in comets by mass spectrometers aboard spacecraft. The Rosetta mission, which accompanied the comet 67P Churyumov-Gerasimenko from 2014-2016, conducted the most detailed analysis yet of a cometary nucleus. Its Rosina mass spectrometer detected glycine, the simplest amino acid, and phosphorus in the cometary coma, alongside dozens of other organic compounds. The implication is that the chemistry needed to get life started is not concentrated uniquely on Earth or even in the inner solar system, but is present throughout the molecular inventory of the nebula from which the solar system formed, and presumably throughout other star-forming regions across the galaxy. The question of how chemistry becomes biology, how a collection of organic molecules in a liquid environment crosses the threshold into self-replicating, metabolizing, evolving systems, remains one of the deepest unsolved problems in science. The origin of life on Earth is not understood in mechanistic detail. We know that life was present on Earth by at least 3.5 billion years ago based on microfossils in ancient Australian rocks, and possibly earlier based on isotopic signatures in even older sedimentary deposits. The Earth itself formed 4.5 billion years ago, and the period between formation and the earliest evidence of life was apparently short by geological standards, a few 100 million years at most. Whether life arose quickly because the chemistry is not difficult given the right conditions, or whether the Earth was unusually lucky in the timing of a rare event, cannot currently be determined from a single example. The study of extremophiles, organisms that thrive in conditions previously considered incompatible with life, has progressively expanded our picture of the range of environments where life is possible. Thermophilic bacteria and archaea have been found in deep-sea hydrothermal vents at temperatures exceeding 120 degrees Celsius. Psychrophilic organisms survive and metabolize in sea ice at temperatures well below zero, in brine channels where the salt concentration keeps the water liquid. Acidophilic organisms live in environments with pH values near zero, conditions acidic enough to dissolve metals. Deinococcus radiodurans, sometimes called the world's most radiation-resistant organism, survives doses of ionizing radiation thousands of times higher than would kill a human, repairing its fragmented DNA through a remarkably efficient molecular repair system. The existence of extremophiles does not tell us that life exists in the extreme environments of other planets, but it tells us that the boundaries of habitability, at least for Earth life, extend significantly beyond what was assumed before extremophiles were systematically studied. Subsurface liquid water maintained by tidal heating, as in the cases of Europa and Enceladus, and possibly Titan, is now considered a plausible environment for life, not because we know life is there, but because the conditions are not obviously incompatible with Earth-based biochemistry. Enceladus, a small icy moon of Saturn, has become one of the most compelling astrobiological targets in the solar system. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through plumes of material erupting from the moon's south polar region and detected water ice, water vapor, molecular hydrogen, carbon dioxide, methane, and complex organic molecules, including compounds that on Earth are associated with hydrothermal activity. The molecular hydrogen is particularly significant. It is produced on Earth by the reaction of hot rock with water in a process called serpentinization, which also produces compounds that serve as energy sources for microbial communities at hydrothermal vents. If the same chemistry is occurring in Enceladus' subsurface ocean, there is a plausible energy source for microbial life. Whether it is sufficient and whether life exists there, we do not know, but the ingredients and the energy source are demonstrably present. Europa, the fourth largest moon of Jupiter, has a global subsurface ocean of liquid water beneath an icy crust, maintained by the intense tidal heating from Jupiter's gravity. The ocean is estimated to be 60 to 150 kilometers deep, containing more liquid water than all of Earth's oceans combined. The Hubble Space Telescope has detected plumes of water vapor erupting from the surface in several locations, suggesting that the subsurface ocean communicates with the surface in at least some places. The Europa Clipper spacecraft, launched in October 2024, will make dozens of close flybys of Europa over several years, measuring the composition of the surface and plumes, mapping the thickness of the ice shell, and characterizing the magnetic environment. It will not land or drill through the ice, but it will provide the most comprehensive dataset yet on whether Europa's ocean has the chemical properties that would support life. The detection of life, if it exists anywhere in the solar system beyond Earth, would be a discovery of incalculable significance, not merely scientific but philosophical and cultural. A second independent origin of life, even microbial life, within a single stellar system would have profound implications for the frequency of life in the universe. If life arose twice in the same solar system, the probability that it arises elsewhere, wherever conditions are suitable, becomes much higher. Conversely, if exhaustive investigation of every potentially habitable environment in the solar system returns no evidence of life, that null result is itself informative, though more ambiguous, since we cannot rule out that life is present in a location or form we did not examine. The search for life beyond the solar system operates on entirely different principles and at entirely different timescales. We cannot send spacecraft to nearby stellar systems in any human lifetime, and we cannot yet resolve the surfaces of exoplanets. What we can do is analyze the light that passes through or is reflected from exoplanet atmospheres, searching for molecular signatures, spectral fingerprints of gases that would not be present in the absence of biological activity. The most discussed biosignature is oxygen. Molecular oxygen is chemically reactive. It combines readily with rocks, organic compounds, and other atmospheric gases, and would rapidly disappear from an atmosphere in the absence of a continuous source. On Earth, the source is photosynthesis. The atmosphere's 21% oxygen content is entirely biological in origin. Before the evolution of photosynthetic life, roughly 2.4 billion years ago, during the period called the Great Oxidation Event, Earth's atmosphere contained essentially no free oxygen. Its presence in an exoplanet's atmosphere would therefore be a strong indicator of biological activity, though not a definitive one, since abiotic mechanisms for generating small amounts of atmospheric oxygen exist, particularly involving the photolysis of water vapor. Methane is another candidate biosignature, particularly if found in combination with oxygen. These two gases react with each other and cannot coexist in large quantities over long time scales without a continuous source of both. On Earth, methane is produced by methanogenic archaea, a group of microorganisms that live in anaerobic environments, including swamps, wetlands, and the digestive systems of ruminants. The simultaneous detection of substantial methane and oxygen in an exoplanet's atmosphere would be very difficult to explain by purely abiotic chemistry and would constitute strong, though still not conclusive, evidence for biology. The James Webb Space Telescope has already detected carbon dioxide, water vapor, sulfur dioxide, and other molecules in the atmospheres of exoplanets. Its spectroscopic capability in the infrared allows it to identify molecular absorption features during transits. The atmospheres characterized so far are mostly those of hot Jupiters and warm Neptunes, large planets with extended atmospheres that produce strong signals. Detecting the thin atmosphere of an Earth-sized planet around a Sun-like star is beyond Webb's capability. But for planets around small red dwarf stars, where Earth-sized planets in the habitable zone transit more frequently and produce larger signals relative to the stellar disk, Webb can in principle detect atmospheric features. The TRAPPIST-1 planets are the prime targets, and dedicated observing programs are underway. The next generation of extremely large ground-based telescopes, the Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope, will have substantially better capability for direct imaging and high-resolution spectroscopy of nearby exoplanets. Direct imaging, rather than transit spectroscopy, involves blocking the light from the star and detecting the much fainter reflected light from the planet directly. This requires extraordinarily precise coronagraphs and wavefront correction systems. For nearby stars within a few tens of light years, the angular separation between star and planet may be large enough to permit direct imaging with next-generation instruments. The contrast ratio, the ratio of the star's brightness to the planets, is roughly 10 billion to 1 for an Earth-like planet around a Sun-like star. This is the technological challenge that coronagraph developers are working to overcome. A space-based mission specifically designed for this purpose, currently called the Habitable Worlds Observatory and under consideration by NASA as a large strategic mission for the 2040s, would combine a large primary mirror with an advanced coronagraph capable of imaging dozens of nearby Earth-like planets in reflected starlight. Its spectrograph would search for oxygen, water vapor, ozone, and methane. If the mission is built and operates as planned, it would for the first time put the search for atmospheric biosignatures on a systematic, statistically meaningful footing. The question of whether technologically sophisticated life exists beyond Earth, not just microbial life, but civilizations that might communicate across interstellar distances, is addressed through an entirely different approach. The Search for Extraterrestrial Intelligence, or SETI, has been scanning the radio sky for artificial signals since Frank Drake conducted the first systematic search, Project Ozma, in 1960. 60-plus years of searching have produced no confirmed signal of extraterrestrial origin. The most famous candidate, the WOW signal detected by the Big Ear Radio Observatory in 1977, was a strong narrowband signal in the frequency range expected for interstellar communication, but it was never repeated in spite of many subsequent observations of the same region. Its origin remains unknown. The silence of the radio sky in the face of decades of searching is one piece of evidence relevant to the Fermi paradox, the observation that, given the age and size of the universe and the apparent abundance of potentially habitable environments, the absence of any detected sign of extraterrestrial civilization is puzzling. Various resolutions have been proposed. Technological civilizations may be genuinely rare, either because the origin of life is rare, or because the evolution of intelligence is rare, or because the development of technology is rare, or because technological civilizations tend to destroy themselves before becoming capable of interstellar communication. Alternatively, civilizations may be communicating in ways we are not looking for, or may not be transmitting in our direction, or may have passed through their radio communicating phase so quickly that we are statistically unlikely to have caught any of them in it. None of these explanations is uniquely compelling. The Fermi paradox remains a paradox. What can be said with confidence is that the universe is very old, very large, and contains conditions conducive to chemistry of the kind we associate with life across an enormous range of locations and epochs. The first stars formed less than 400 million years after the Big Bang. They lived and died, enriching the gas from which subsequent generations of stars and planets formed. By the time the Sun and Solar System formed 4.6 billion years ago, roughly 9 billion years after the Big Bang, the galaxy had already hosted many generations of stellar evolution. Billions of planets may have preceded Earth in the history of the Milky Way, some of them rocky, some of them orbiting at habitable distances from their stars, some of them potentially with oceans and atmospheres. If life is a generic chemical outcome given the right conditions, it may have arisen and evolved on many worlds long before Earth existed. What became of those potential civilizations, whether they exist, whether they persist, whether the universe contains remnants of intelligences that arose and flourished and perhaps perished billions of years before our own species appeared, is a question that current science cannot answer, and may not be able to answer for a long time. What science can do is narrow the range of the unknown. Each exoplanet characterized, each atmospheric spectrum obtained, each icy moon flyby completed, each gravitational wave detected, each supernova remnant mapped, each molecular cloud imaged. All of it adds to a picture of the universe that becomes incrementally more precise and more complete. The project is not moving quickly by human standards. Individual discoveries come and go on the timescale of years or decades. But measured against the timescale on which the universe operates, measured against the billions of years during which stars have formed and died, galaxies have merged and separated, and planets have acquired and lost atmospheres, the pace of human scientific progress is extraordinary. We have gone from believing the Earth was the center of a finite cosmos to knowing our galaxy contains hundreds of billions of stars, and that the observable universe contains hundreds of billions of galaxies in a span of roughly 4 centuries, from not knowing that atoms exist to imaging the shadow of a black hole in roughly 1 century. The trajectory is one of accelerating capability applied to problems of increasing difficulty, and there is no obvious reason to think it has reached its ceiling. The largest stars in the universe will not last long enough to witness whatever comes next in that project. A hypergiant burns so intensely, converting mass to energy so rapidly that its entire lifespan fits within a time interval shorter than the period that has elapsed since the first anatomically modern humans walked the earth. VY Canis Majoris will explode within the next 100,000 years, soon in astronomical terms. A nearly incomprehensible future from any human perspective. When it does, it will briefly outshine the entire Milky Way. Its light will take roughly 3,900 years to reach Earth. Observers who see it, if anyone is watching from here or anywhere at that moment, will witness the death of something that was burning before the first cities were built, before the first written languages were invented, before the first domestication of animals. The light arriving at that moment will have been traveling across space since before human civilization existed. That is the scale on which stellar physics operates. It is the scale against which all human timescales are measured and found brief. And it is precisely the scale that makes the project of understanding the universe both humbling and, in a way that is difficult to fully articulate, deeply compelling. We are small and short-lived, and our instruments are primitive by the standards of what we are trying to measure. And yet the measurement continues year by year, observation by observation, each new result revealing a universe stranger and more detailed and more intricate than the one that preceded it. The stars do not care whether they are understood, but we do. And that distinction between the universe as it is and the universe as it is known may itself be among the most remarkable things the universe has produced.